Hello and welcome to Gaffy's Grinds. This is video 8 in our series on radioactivity for Leaving Cert Chemistry. The usual reminders: if you've got your phone on you, turn it off or stick it on silent now so it's not going to distract you. Close any open tabs or social media that you've got open. And the main thing is that you listen carefully when I give the explanations and that you do the practice questions when I give you things to do. If you're not going to do them, then you're really wasting your time watching the videos. Today's lesson is the final lesson in this particular topic. We're going to talk about why it is that we're actually interested in radioactivity. So as scientists are interested in radioactivity because it gives us kind of clues as to help us understand what atoms are really like. So for example, Rutherford was the first guy to, I suppose, use radioactivity in this way when he took alpha particles, fired them at some gold foil and figured out that most of the atom is actually empty and you've got some hard dense nucleus in the middle. So that was Rutherford's discovery using alpha radiation. And of course, since atoms are too small for us to see, even the most powerful microscopes, we can only try using some experiments to work out what they're really like. So we work backwards for some clues to build up our understanding and our models of the atom. Now, studying radioactivity also gives us information, can give us information about our universe, the history of our universe, what happens inside stars. So if we can study the radiation that's coming from deep in space, we can figure out what's going on out there in space, what's happened actually in the past, because a lot of radiation is left over from events that happened millions of years ago, and it's only reaching Earth now because it's had so far to travel. It's important to understand radioactivity, though, especially if we're going to try and use it, because when we come into contact with it without protection, it can be quite dangerous. So it can increase our risk of cancer, for example. So we do need to understand it, understand what we're dealing with, understand the safety concerns. So by using radioactivity in experiments, scientists can find out about causes of cancer and processes of how cancer works, and also work on potential cures for the diseases. So radiation can even be used to treat or to target tumors or cancers and get rid of them. Okay. Now, radioactivity also has many useful applications in things like medicine, industry and engineering, and in this video we're going to take a look at a couple of those. So the first thing we're going to talk about is we are going to talk about a device that we should all have in our homes, and if you don't, then you really need to get a couple of these, and they're really important when you have your own homes. It's so important that you keep these in your homes, and they are fire alarms, smoke alarms. Okay, so a smoke alarm is essentially a plastic casing. Okay, and the plastic casing has holes in the bottom, okay, like this. Now, what goes on inside a smoke alarm is that generally we will have two main components. This component here is actually a source of radiation, and it's a source of alpha radiation. So it's an alpha radiation source. So what this would be is it would be a substance that contains some radioactive isotopes. Now, a very common radioactive isotope used in a fire alarm is the isotope americium 241. So americium atoms with a mass of 241 are a very common source of alpha radiation, and we use them in fire alarms. Now, that is something that you guys need to know. You need to know that americium 241 is a classic source of alpha radiation, and it's typically what we find in fire alarms. Now, the general gist of how a fire alarm works is that there's a second component here, and the second component is basically a radiation detector. So this is a radiation detector. The radiation detector obviously does what it says, it detects radiation, but the radiation detector has a circuit, an electric circuit that's connected to an alarm. So it's connected to the alarm circuit. Okay, and what generally happens is that the alpha radiation source is constantly firing alpha radiation at the radiation detector, which is all good. That's what's supposed to happen. Okay, so it's constantly firing alpha radiation at the radiation detector. This is a plastic casing. that we have around the outside of our fire alarm. Doesn't really just houses the rest. I suppose the rest of the what's inside. It doesn't really have any other function. But so long as the radiation is hitting the radiation detector, the alarm will not go off. So this is the way it's supposed to be. Alpha radiation constantly firing at the radiation detector. So this is alpha radiation. And the alpha radiation hits the radiation detector. And so long as it does that, then there's no issue. Okay, the alarm will keep functioning as normal. It won't be making any noise. So what happens is, if there's a fire and we get smoke particles, which I'm going to show in blue here, we get smoke particles coming from a fire in a home. Well, what happens is they're going to enter the fire detector. And when they enter the fire detector, they start to move between the alpha radiation source and the detector. And what begins to happen is that the alpha particles, because remember, alpha particles are the lowest penetrating radiation, which means they can be stopped by air, by thin sheets of paper, for example. So smoke particles is enough to block them from ever reaching the detector. So what happens is that they still travel, but they get blocked by the detector. Now, if this was any other type of radiation, like beta radiation or gamma radiation, these would be much more penetrating and they would not get blocked by the smoke particles. They would just travel through them. They would pass straight through them. But the alpha radiation gets blocked by the smoke particles. And when this happens and the smoke particles block the alpha radiation, now the alarm circuit is triggered and the alarm starts to beep or make noise or whatever, however you would describe it, buzzes or beeps. That's what happens when you hear the smoke alarm going off. If you might have heard it when your parents were cooking before, when you were cooking yourself and there's a lot of smoke in the kitchen, you set off the fire alarm. What it is the smoke particles block the alpha radiation, and this causes the alarm circuit to trigger and you get the noise from the smoke alarm. So the radioactive source used here is americium-241. It's a classic source of alpha radiation. We find its uses in a smoke detector. All right, you ready to do some questions, practice questions on that now? So these following questions are about smoke detectors. So what I want you to do is I want you to pause the video. I want you to read the questions and answer them, please, and play for the answers. Okay, so a reminder, you should only be watching the video now if you've done the questions. Answers are going to be coming up. There's no point in watching these videos if you're not going to do the practice, you're not going to learn anything, so make sure you do them. So the smoke alarm stays off while alpha radiation reaches the detector. Why does the alarm switch on when smoke particles enter the plastic casing? Okay, so hopefully here you mentioned something about the alpha particles cannot penetrate the smoke particles. Okay, so the alpha radiation is blocked or cannot penetrate the smoke particles. So they are blocked. Okay. And if the alpha radiation is not reaching the detector, then the alarm goes off. Okay, so hopefully you said something like that. I'm not going to say exactly what phrasing you should have, but I've told you the key parts you should have in your answer. B, why is it safe to use a source? Why is it safe to use a source of alpha radiation in the house? Okay, I didn't directly mention this today, but we have gone through this before. Well, obviously, how is it safe to use this in the house? Well, it's got a very low penetrating power. So if it's got a very low penetrating power, then there's always going to be a few centimeters of air at least between you and the fire alarm. So I wouldn't be going putting it in your mouth or anything, or holding the smoke detector right up to your eye. I wouldn't be going doing anything like that. That wouldn't be very clever. You're really best off, only go near it if you need to change the battery or test the battery or whatever. You don't need to be afraid of it, but I wouldn't be going swallowing the components of it or anything like that. It's safe to use in a house because it's got low penetrating power, which means it's stopped by a few centimeters of air. So it's no big deal. The smoke alarm would not work with radiation source that emits beta or gamma radiation. Explain why. Well, hopefully you've mentioned something about smoke particles would not stop or block beta or gamma radiation. or you could say beta and gamma radiation are more penetrating than alpha. The smoke particles would not stop beta or gamma radiation. Name the source of alpha radiation in a smoke detector. That would be americium 241. Well done, you said that. Americium, named after the country America, obviously. Americium, and it's 241 is the isotope. Well done. Okay, so that was how do we use a source of alpha radiation? We're going to take a look at this now. Okay, what you see here is you see a scientist doing an aging test or a dating test on a sample of bone. This here is something that we call carbon-14 dating. So obviously it's going to involve isotope carbon-14. And it's a dating technique that we can use to figure out the age of a specimen which was once alive. So for example, this bone obviously came from something that was alive. Now, how does it work? How do scientists use this? Okay, so what I'm going to do is I'm going to show you basically what happens. How does carbon-14 dating work? Well, if we take, for example, a living thing like this, whatever this bone came from, or a tree. It's easy to work with a tree, I think. A tree is made mostly of carbon. Where does it come from? The carbon comes from the carbon dioxide taken in by the tree. It basically breathes in carbon dioxide from the air, and it's constantly taking in carbon and takes it in from the air. Now, obviously, in the air, there is a natural abundance of carbon-12, carbon-13, carbon-14. Okay, so some of the carbon atoms in the air and the carbon dioxide that's in the air, most of them are carbon-12, some of them are carbon-13, some of them are carbon-14. Okay, so now the tree doesn't know which one is which, it just takes in carbon dioxide. And some of those molecules will have carbon-12, some of them have carbon-14. It doesn't really make any difference to the tree when it's alive, it's going to use them. So if we was to draw here, if I was to draw the carbon-12 and carbon-14, I'm going to draw the carbon inside the tree. So what I've got here is I've got 1, 2, 3, 4, 5. Just going to draw here first some blue particles that represent one isotope of carbon. And then I'm drawing some orange particles which represent a different isotope of carbon. Okay, so you see what I'm doing? All together here, I'm drawing 25 atoms. Now, obviously, a tree has a lot more than 25 atoms. I'm just doing a simple example to try and help you understand the ratios of these. So if we were to look at the orange atoms and say that orange atoms represent carbon-12. Now, the carbon-12 is the stable isotope of carbon. It's stable, it's never going to decay, it's never going to break down. Carbon-14, this is a radioactive isotope that undergoes beta decay. Carbon-14 is unstable. We know already that means it's going to decay, break down, and become, it's going to decay by beta decay, basically. Now, because the substance is alive, this tree is alive, it's always taken in carbon. So it's always maintaining this ratio because it's taken carbon dioxide from the air. And like I said, in the air, there's a natural amount of carbon-14 and carbon-12. So in this particular example, we have 15 carbon-12 atoms, and we have 10 carbon-14 atoms. Now, I don't know if that's the exact ratio of carbon-12 to carbon-14 that's in the air, but I'm trying to use this as a simple example. So if the ratio of carbon-12 to carbon-14 in the air is 15 to 10, we'll say, so 15 carbon-12 for every 10 carbon-14s, then so long as the tree keeps alive and keeps taking in carbon dioxide from the air, we're always going to maintain that same ratio because that's the ratio of carbon dioxide, these two carbon isotopes that exist in the real world everywhere. So, on average, these are the ratios. So long as the tree is alive, it will maintain this ratio. The thing is, what happens when the tree dies? When the tree dies, it stops taking in carbon dioxide. It stops doing photosynthesis and taking in carbon dioxide. And when that happens, well, the carbon-14 is going to start to decay. Okay, so we say after a certain amount of time, we now have, just going to go back here, say we now have, instead of 10 carbon-14 atoms, we now have 5 left. Okay, so what do we call the amount of time that must have passed for us to go from 10 carbon-14 atoms to 5 carbon-14 atoms? What do we call this amount of time? On 3, speak your answer to the screen. 1, 2, 3. We call this time 1 half-life. Well done, you got that right. That's from a previous video. We know that the time taken for half the radioactive nuclei to decay in a sample is called half-life. So we say 1 half-life has occurred. Now this is beta decay, which means that we know what's going to happen. One of the neutrons is going to basically turn into a proton and kick out a beta particle. Now what's left behind is not carbon-14. It's not a carbon nucleus anymore. Instead, it has been mutated or changed. So the nucleus has changed, and we now have a different element. So we have what we call transmutated the element. We don't have carbon anymore. So all the ones you see in green are ones that have turned into a different element. And the different element that they've turned into, if it was carbon-12, we now have if it was carbon-14, sorry, we now have nitrogen-14. So carbon-14 has turned into nitrogen-14. Now, of course, the rest that were already carbon-12, well, they're still carbon-12 because those were stable isotopes. Those are never going to break down. So those are still carbon-12. Like that. Okay, so now what we have is we have our, sorry, it's crashed. I'm going to have to pause the video for a second. And we're back. Okay, so obviously all of the nuclei which were already carbon-12, well, those were stable, so they were not going to decay. So what's left is we've still got our 15 nuclei of carbon-12, but we have now reduced to 5 nuclei of carbon-14. So obviously here, the ratio of carbon-12 to carbon-14 has increased. We now have a bigger ratio of carbon-12 compared to carbon-14. So scientists can basically take a sample now, so say it's this bone here, and they can measure how many nuclei of carbon-14 are left. And by knowing the ratio of carbon-12 to carbon-14 when an organism is alive, so when they would be constantly taking in carbon from the atmosphere, by knowing that by knowing that natural ratio and knowing how many there are now, they can figure out how many half-lives have occurred. So here we've shown 1 half-life. Now there might be a lot bigger ratio of carbon-12 to carbon-14 left now. So the key thing is to work out how many half-lives have gone past. And we do this, and when we do this, we can work out how many years that is, because scientists know that the half-life of carbon-14 is 5,730 years. So scientists know that every time the carbon-14 nuclei half compared to what they should have been when it was alive, that means 5,730 years has gone past. So by using this technique, they can get a rough estimate of how old something is. So bearing in mind that carbon-14 is a classic source of beta radiation. And it's used radiation. And it's used for what we call, or we say, to date artifacts, which are just really old objects of interest. So it's used to date artifacts. So things like diaries and books, we can use carbon-14 dating. Because books came from a tree, we can check the paper and see how old it is, and that gives us an idea of whether, if a diary is saying it's from 7,000 years ago, and we do carbon-14 dating on the paper and find out it's only 100 years old, then we know it's a fake. Okay, so it's really important to be able to do that and figure out how old things are, give you an idea about history. All right, it's time to do some practice now. All right, so what I want you to do is I want you to pause the video and I want you to answer these questions now, please. Okay, so first of all, true or false? The ratio of carbon-12 to carbon-14 is constantly changing when an organism is alive. That is false. It does not change. Okay, so the organism is constantly exposed to the natural abundance of each of these isotopes in the atmosphere, which is pretty stable. So when we breathe in, or when a tree takes in carbon dioxide, or when we eat plant material, we always are taking in the same amount of each type of this carbon. So that keeps our bodies stable, keeps the ratio the same while we're alive. Anything that's alive will have the same ratio of carbon-12 to carbon-14 until you die, and then you don't stop taking in carbon, and only the carbon-14 breaks down, then the carbon-12 stays stable. What happens to isotopes of carbon-14 after the organism dies? They undergo beta decay. So if you just said they break down, then that's not specific enough. What type of radiation? Well, I suppose that's the next question anyway. So what happens to isotopes of carbon-14? They break down, or they decay. It's probably a better word. Decay. What type of decay? That would be beta decay. And how do scientists work out the age of an artifact? So you should be mentioning half-life in your answer here. So they work out how many half-lives have occurred. How many half-lives have occurred? Okay, so they know how many atoms is in a sample. They know how many atoms they should have of carbon-12 and how many they should have of carbon-14 when the atom was alive. Then they work out how many I actually have, and that tells them how many half-lives have passed, and they can work out how old something is. Okay, so that's beta decay, using beta decay in a process. But the next thing we're going to look at is something called the irradiation of food. Okay, so irradiation of food. So what I'm drawing here is, I'm going to try draw them a little bit better than that. Okay, so I'm drawing here. Jesus, that's bad. All right, these are supposed to be strawberries. Okay, so you have to forgive me. Okay, so these are strawberries, believe it or not. Okay, so I'll color them in red really quickly. These are 3 strawberries. Okay, and we'll give them little green tops. And they don't look too bad now. Okay, right. Now say we take our strawberries and we wait for 5 days. We leave them on the shelf for 5 days. What's going to happen to them? Well, what's going to happen to them is they're going to go all squishy. So if I don't eat them after 5 days, they're going to go all squishy, and they're basically going to rot. Okay. And the reason for this is the bacteria inside them are going to feed on them, and they're going to rot them. Okay, so you've got your strawberries, and they're basically going to be shriveled and rotten and not very nice. Definitely not edible. Okay. The other option is you can take your strawberries, okay, and you can use gamma radiation. So you can basically fire them with gamma radiation. Now, how can we do this? Well, we need to take a source of gamma radiation. Spell it right, gamma radiation. Now, a classic source of gamma radiation is an isotope called Cobalt 60. So we take Cobalt 60 and we use the gamma radiation that comes off it. Then after 5 days, what happens is we still have nice fresh strawberries. Okay, so we're using gamma radiation as a method of preserving food. So here is my strawberries and they are still nice and fresh. And they're still edible. So we say we've given them a longer shelf life. Okay, so you've got your fresh strawberries, still fresh after 5 days or so. Okay, so what's happened is we've added gamma radiation. We've added gamma radiation. And what the gamma radiation has done is, the key thing is it's killed bacteria. Now, generally in food, if we want to kill bacteria, we generally tend to cook things. So we add heat. If we add heat, we can kill bacteria because they don't like heat, especially if you heat things up hot enough. Like if you take chicken, you put it on a pan, a really hot pan for like 5-10 minutes, you kill all the bacteria and you make it safe to eat. But you don't really want to do that with strawberries. Okay, you don't want to cook your strawberries, you want fresh strawberries. So by adding gamma radiation, we can kill the bacteria without cooking the food, without warming it up. So in that case, we don't really want to cook our strawberries. So the big advantage here, I suppose, is that food can last for longer. Food lasts longer. So say the potential, I get some people are afraid of like using radiation with food and all of that, but really like the radiation doesn't stay in the food, it just passes through it and it kills the bacteria. It doesn't actually get stuck in it and then you eat it and you're taking in the radiation. It doesn't work like that. It passes through it and it just kills the bacteria. So obviously, if it can help us food last longer, then we have less food to throw out with less food wastage, which means like we don't have to go and buy more and take food away from other people who might need it. So again, it's a possible solution to stop us throwing things out when there's other people who don't have enough to eat. So it saves us on food waste. So we get less food waste, which is obviously desirable because it really isn't good that in the Western world we throw out so much food when other parts of the world have nothing at all to eat. Okay. It doesn't make food more radioactive. It does not do this. It does not make food radioactive because, like I said, it doesn't get stuck in the food. It just passes through it, kills the bacteria. So it does not make food radioactive. Make food radioactive. So that's not going to be a big issue. And if we try to use heat, it would cook the food, which is fine for some foods, but not things like strawberries and fruit. And fresh food we generally don't want to be cooked. Another way we can use gamma radiation, we could use Cobalt 60, is on things like medical equipment. So if you've got medical equipment and you've done a surgery, you can basically take that medical equipment like scalpels and knives and you can put them in a bag, a special bag that's designed for irradiating. So this word irradiation. So irradiating, we can also irradiate medical equipment. Okay, so again, you take your gamma rays and you pass them through the bag of medical equipment. And this is gamma radiation, shown in the green line, gamma radiation. And these are medical equipment. This is medical equipment. And again, the advantage here is that you kill any organisms like bacteria or fungi that might be growing on them that might infect the next patient that they're used on. Now, again, so the other option here is to use very high temperatures to sterilize equipment. And that's okay. But again, some pieces of equipment might be made out of might have plastic handles or might have wooden handles, or they might have like rubber pieces in them and things like that. And if you use heat, then you're going to melt them, you're going to change their shape, you're going to stop them from being effective. So again, irradiation using gamma rays can kill all bacteria without heating them up and like distorting or melting the equipment that might not be suitable for using for heat. So if it's just something made of metal, then generally it's no issue to just throw them in and heat them up. But irradiation is is a simpler method. It's quick, doesn't take loads of time. It just a few seconds, give it a blast, and it's done. And it kills all bacteria. So generally, irradiation of medical equipment is another way we can use gamma radiation. And again, too much heat could damage the equipment. So these are two ways in which irradiation can be used. Irradiation of food and irradiation of medical equipment is gamma radiation. Okay, so, and a source of gamma radiation is Cobalt-60. So you must know your sources and you must know your uses. All right, so it's time to do the last practice set today. Okay, so here we are. All right, let's take a look at question 1. What you have to do in question 1 and 2 is you have to select which one of the 3 answers is correct. Okay, I hope you can see that they're in like a table of 3, and you have to just write down which one is correct. And then question 3, 4, and 5, you have to answer them. Please do that now. Okay, so you should only be watching if you have answered the questions. First of all, gamma rays are, what are they? Okay, so they are not ionizing particles because they are not a particle. They are not non-ionizing electromagnetic waves because they are ionizing electromagnetic waves. So that was the correct one. Well done if you said that. What do gamma rays do to bacteria? Well, they don't warm them, they do kill them, and they don't cook them. Okay, so other things are talking about heat. So irradiation, gamma rays do not do that. They don't warm them, they don't cook them. What happens when you irradiate fruit? Well, it kills the bacteria, and increases shelf life, something like that. So it makes it last longer. Okay, so it kills bacteria, makes it last longer, increases the shelf life. Give 2 uses of gamma radiation. So that would be food irradiation and sterilizing medical equipment. Well done if you said that. Excellent. And the last one, which radioactive isotope can be used as a source of gamma radiation? That would be Cobalt-60. Okay, great job. Well done if you got that right. If you found this video useful, do leave us a like down below. It helps other people to find the channel. If you want me to make any videos for you in the future, if you have a topic that you're struggling with, do leave a comment down below. And that is the end of our chapter on radioactivity. So I hope that you stuck with me the whole way through and that you found them easy to follow. You should be able to answer any question that comes up now on the Leaving Cert chemistry paper on radioactivity. Comes up usually as a half question, so 25 marks out of 50, and it's generally quite a nice question. They're very samey, there's not that much in it, so I mean, if it comes up as a question, then I will be pretty happy with that. Okay, all right, thanks for watching, guys. I'll see you in the next video.